All right, so this is a follow-up video from the first video on linear equations, part 2 out of 3. In the last video, we just talked about kind of how linear equations work, what they are, what they mean. Now we've figured out how to use a table. That's kind of what we worked with up to this point. We're going to talk about how we can turn that table into a graph. So let's take, for example, we've got this, let me get a color that'll stand out. We sort of started off, we had this problem in the last video. I'm going to show it real quickly, where we talked about a bicyclist traveling at 3 miles per hour. And so we said, okay, well, if they don't travel at all, then they won't travel any distance. And if they travel for 1 hour, 3 miles, 2 hours, 6 miles. And we compiled this table to just show the relationship between how long they cycle versus how far they travel. Now, what if we wanted to know more about this situation? What if we wanted to know how far they'll travel in an hour and a half, or in 5 hours, or in 10 hours? This is where a graph really comes in handy, because it shows us all the points that are within range of the graph. We use two number lines here. We have our x number line. And depending on how far left or right we are on this number line, that's telling us the value of our x value. In this specific scenario, it was about how long the cyclist traveled. Then we have this other number line that moves up and down. And this shows us our y value, or our output, which in this case was how far they had traveled. So the very first point, we could say, was if the cyclist didn't travel any time at all. And we determined that that meant that they will have traveled 0 distance. So we're going to put a point here. On our number line, this is 0 left and right. These are the negative numbers. These are the positive numbers. And up and down, this is 0. These are the positive numbers. These are the negative numbers. Now, after 1 hour, so we're going to move over here to 1 hour. This is the 1 value on our input number line, or our x number line. And we notice that the output is 3. So when we move over 1, then on our y value, 1, 2, 3, we're going to be at 3. So we put a point here. Then we say, okay, after 2 hours, so we're going to come over here to 2, we can see it's 6. So there's 3, 4, 5, 6. So we're going to put a point here. And then after 3 hours, it's going to be 9 miles. So we see that our distance, which is what goes up and down, moves up 3 every time that our time goes over 1. And now we can connect these, right? And I'm sorry, I'm not very good at drawing the straight line here. We're going to connect these and say that this goes on forever, right? So now we can see that at half an hour, we will have traveled 2 miles. And at a third of an hour, these are just a ton. I mean, you can picture this as all of these little bitty points, right? Of every possible x and y value. We can see all of the different points here on this line. And so all that this graph is just a way of representing the data that we've already put together from our table. We can do this for any equation. So let's take the equation 3x minus 4. This is a linear equation. So our inputs, we're given a couple of inputs here, and we're asked to fill this table out. This is our function, right? 3x minus 4. And then our solution, which is our output, is what we're going to fill in here. So you can kind of get a paper and follow along with the math if I move a little bit too quickly. But if we have negative 2, then 3 times negative 2 is negative 6. And then we subtract 4, that's going to be negative 10. We put a negative 1 in. 3 times negative 1 is negative 3. Negative 3 minus 4 is going to be negative 7. 3 times 0 is 0 minus 4. We get negative 4. 1 times 3 is 3 minus 4 is going to be negative 1. And 2 times 3 is 6 minus 4 equals 2. So now that we've completed this table, we can put these points on our graph pretty easily. We can say, okay, so when x was negative 2, if this is 0, that's negative 1, and that's negative 2. Y was negative 10, all the way down here. And when x was negative 1, right, if this is 0, that must be negative 1. Y was negative 7. Now when x was 0, right, when x is 0, we're on the y-axis, right, because we're not left or right of it. We were at negative 4. And when x was 1, we were at negative 1. And when x was 2, we were at 2. So we've plotted these points, and we can now connect those points with this line, right? And in doing so, we're even solving for future points, right? And this line goes up and down, right? And it's important to note, I'm drawing these arrows on each side to show that this could go down forever or up forever. In this previous example, this is going back to the bicyclist, I didn't draw an arrow going down. And this is sort of going back to just kind of using logic for a minute. A bicyclist can't really ride their bike for -1 hours, can they? We can't really, there's no data here because it's literally impossible to ride your bike negative time. Until we learn to like travel through time backwards or something, I guess. You can't ride your bike for -1 hours. So we're not drawing an arrow here. However, in this problem, we don't have any context. This is just this kind of ambiguous function. We don't know what it's about. So we're going to go ahead, since there's nothing that says we can't, and say that this line goes on forever in either direction. So now looking at what we've just done, right? I went ahead and put a real line in. It's a little bit easier, but you'll see the points are still the same, right? -2 and -10, -1 and -7. When x is 0, -4. When x is 1, we're at -1, and when x is 2, we're at 2, right? So this is the same thing as what we drew over here. I just chose to make it look prettier. So I would recommend that you pause the screen and just notice some patterns between this function and this table and this line. And we're going to come back to that. All right, so I'm going to move on here, and I apologize, my computer runs kind of slow when I make some of these videos. I just scrolled down way further than I meant to, and now it's coming back up. I'm not doing that. Where was I? Here we are. Okay. So moving along, we're going to talk about something that's pretty important here. We're going to go back to, there was an example in the previous video where I said that Jose charged $5 every yard he mowed. This means that every 1 yard he mows, he will get $5 out, right? The function is he gets $5 for every 1 yard he mows. So this is this relationship. Every time the input increases by 1, right, which means goes to the right by 1, because numbers on our number line increase when they go to the right by 1. Then his output, which increases going up, will go up by 5. And you can see that this is what controls how steep this is, right? 0 yards, $0, 1 yard, $5, 2 yards, $10. It's this relationship of how high we go every time we go over 1 that determines how steep this line is. This function would be 5x, right? Every 1 yard that we put in, we multiply that by 5, and so this will be 5 times larger than what we put in. If we change the scenario to be $3 per yard, then you could see that every time he mows 1 yard, goes over 1, we go up 3, right? So this line is a little bit less steep. If we kind of go back and forth, you can see that this line is not as steep as that line. And we could even come up with another example of saying, you know, what if he was spending money on gas, right? And his rates were low, and due to how expensive gas was, every yard he mowed, he actually wound up losing $1 because he had to spend so much money on gas. Then the line would be like really not steep. It would actually be what's called a negative slope, right? Because this is going down. Every time he mows a yard, he actually is losing $1, right? 2 yards, he loses $2. 3 yards, he loses $3. The amount that the output changes in terms of how far up or down it goes, relative to how much it changes going to the right, is what we call slope. And visually, this can pretty easily be counted, right? Here's a point. You can see that when we went over 1, we went up 2. When we went over 1, we went up 2. So we can see here that every time we go over 1, every time that our input goes up by 1, our output goes up by 2. So our output goes up by 2 every time our input goes up by 1. And this number, which of course can be simplified to 2, is called slope. If we take the function y equals 2x, we can see that every time our input changes, our output's going to change by twice as much because we're multiplying our input by 2. We can try this. We can say, okay, well, if x is 1, then y is 2. if x is 2, 2 times 2 is 4. Or, I'm sorry, I picked 3 here. Okay, so 3, that's going to be 6, right? And then I picked 7. Well, 7 times 2 is 14. And then I went to 8. Well, that's 16. And then I went to 12. That's going to be 24, right? I just multiplied each of these by 2 because that's what my function said to do. And so I want you to notice here, my input went up by 2, and my output went up by 4, right? Well, 4 over 2, and this gets back to fractions, is the same thing as 2 over 1, which is the same thing as 2, which is what this number being multiplied by x is. Here, my output went up by 8 when my input went up by 4. So I have 8 over 4. Well, guess what? 8 over 4 is still 2. No matter how much my input goes up, that doesn't change the fact that my output's going to be twice as much, right? Here, I only went up by 1, and this went up by 2, which is still 2 over 1. Here, I went up by 4 again, and this went up by 8 again. This is slope. The amount that my output changes, up by 4, over the amount that my input changed. We can look at another one here, and you can probably already guess, since I'm multiplying my input by 1/2, that my output is going to go up by 1 every time my input goes up by 2, right? This is the same thing as saying that my output's going to go up by 1/2 every time my input goes up by 1. But this kind of is annoying to look at, right? You don't want a fraction in a fraction. And so we can just multiply both of these by 2, and we get 1 over 2. So let's try this. That's going to be 1/2, right? If we put 3 into this, well, what is half of 3? That's going to be 1 and 1/2. So my input went up by 1. My output went up by 1 when my input went up by 2. Yep, 1 over 2. That's what we thought it would be. Here, my input went up by 4. So I'm going to guess this is going to go up by 2. What's half of 7? 3.5. Yep, that went up by 2. 2 over 4 is the same thing as 1/2. And we could continue this on. This is going to be 4. And so this went up by 1, and this went up by 1/2, right? When this number in front of x is going, what this is saying is that every time something goes in, half of it goes out. So every time this increases by 1, then this is going to increase by half of 1. Adding this constant here, we've seen some of these where it's like 2x plus 4. Doesn't change anything, right? We can put this in. What's 2x plus 4? Well, when x is 1, that's going to be 6. And when x is 3, that's going to be 10. And when x is 7, that's going to be 18. And when x is 8, that's going to be 20. And when x is 12, that's going to be 28, right? So this doesn't change the fact that my output is still going up 2 every time my input goes up 1. 6 to 10 is 4. This is 2. 4 over 2 equals 2, right? 2 over 1. This went up by 8, and this went up by 4. 8 over 4 is the same thing as 2, right? This went up by 4. This went up by 2. This went up by 1. That's still 2 over 1. That's still 2. Same thing here. So my slope, in general, my slope is simply how much y changed over how much x changed, right? Here, my slope is 1/2. Y goes up 1 every time x goes up 2. And we saw that here, right? This was 1/2. This was 1 and 1/2. That means that y went up 1. That's what this number represents. Every time x went up 2. That's what this number represents. Here, and remembering that this is 2 over 1, right? 2 over 1 is the same thing as 2. Then we can clearly see here that my y, my output, went up 2. That's what that 2 means. Every time my x went up 1, which is what that 1 means. So we're going to stop this video here now that we've talked about what slope is. And I'm going to give you a little problem that I want you to work on. I want you to see here. This is that line we were working with earlier where I told you to pause and look at patterns. And we looked at the fact that This was 1, and when x goes up 1, right? This was our next point. So I want you to look at this, and I want you to figure out what is the slope of this line. Should be a question mark there. I want you to explain the relationship between what slope looks like here, what it looks like here, what we were just drawing, where that goes up 1, and I won't give away how much that goes up, but you can figure it out, and what it looks like here in an equation. I want you to, there's no necessarily right or wrong answer. I want you to just tell me, what do you notice about this pattern of what this looks like, of what this looks like versus what this looks like versus what that looks like. I hope you see some patterns there. You're going to put that in your Google Docs. Thank you so much.